Good morning, everybody. Welcome to the second day of JuliaCon. So I think after the euphoria of last night, we should probably give everybody who was involved in getting Julia 1.0 out another round of applause. And hope that we have many more of the same. So it's my pleasure on behalf of the JuliaCon committee to introduce today's keynote speaker. So Professor Nick Higham is Richardson Professor of Applied Mathematics at the University of Manchester, which is in the north of England. And he's currently also president of SIAM, the Society for Industrial and Applied Mathematics. And he's well known in the field of numerical analysis for his seminal contributions, and he has written several books on the subject. And we're very happy that he's going to be talking about a subject that's dear to the heart of many a Julia programmer, which is tips and tricks for numerical computing.
Okay.
Thanks a lot.
Thank you very much, David. So, as you see from the title there, yes, I'm going to try and tell you some ideas that are hopefully timely, fairly simple, but also fairly useful. So I chose the title because it's very short. It's always good to have a short title. I then wondered what actually is a trick. And then I remembered the quote from Pollier, a trick used 3 times becomes a standard technique. So you can see a list of the ideas I'll be talking about at the top there, ranging from complex arithmetic, exploiting that, to a few points about multi-valued functions. I'll talk about associative matrix products and how that's hidden behind the scenes, but actually very important. A brief word about randomization, and then I'll talk a little bit at the end about floating point arithmetic, and in particular, low precision arithmetic, which I think is an interesting topic at the moment and very timely. So let me begin with a topic that you'll find in almost any numerical analysis textbook, which is differentiation, numerical differentiation. So we have a function f, and we'd like to approximate its derivative. And what you see there is the standard forward difference. So we take a small h, and we look at the difference of f of x plus h minus f of x over h. Of course, as h goes to 0, that converges to f dash of x. And we hope that for small h, we can get a good numerical approximation. The error is big O little h for smooth enough f. If you try this in practice, here's what you might see. So this is done in IEEE double precision arithmetic, where we have about 16 decimal digits worth of significance in our numbers. So you'll see some h's on the bottom there. This is for f of x is e to the x, and I've taken x is 1. And you can see that the error shown on the y-axis does decrease, although somewhat erratically. But then at some point it starts to increase again. So we hit that sort of dotted red line, and then basically the error starts to blow up. And of course, this is a well-known phenomenon, this so-called V-shaped curve, and it's due to cancellation. It's due to the floating point arithmetic, the errors in the evaluation starting to dominate the truncation errors that mathematically are going to 0. And so what is the point at where the minimum is reached? Well, roughly, approximately this value of h shown here. Unit round off, about 10 to the minus 16, mod f of x divided by the mod of the second derivative. So this is a well-known thing you'll find in most textbooks. And so, at least with this simple formula, you're limited to how much accuracy you can get in your approximation. So the question is, can we do better? Of course, you could do something like automatic differentiation. I want to stay numerical. So here's another thing we can do.
Automatic differentiation is numerical.
Okay, so this is very different. What I'm going to do is perturb my x by a multiple of the imaginary unit I. So I look at f of x plus ih. So I'm assuming everything's real. F is real, x is real. But I'm now going into the complex plane. Evaluate f, divide by h, and take the imaginary part. So if you've not seen this before, this certainly seems rather weird. And the claim is that that will give you a good approximation to the derivative. In fact, the error will be big O h squared. It's quite easy to prove. You just expand f in a Taylor series and equate real and imaginary parts, and this all comes out rather nicely. So how small should you take h now? Well, you can take h as small as you want. This idea has been used at the National Physical Laboratory down the road in Teddington, Middlesex for many years, and they take h is 10 to the minus 100. Any small value of h will work, and you will get an accurate answer. So the point is, rounding errors now are not a problem. There's no cancellation here. The only caveat is that your algorithm for evaluating f must not involve complex arithmetic, because if it does, you'll get a resonance between the rounding errors in that evaluation and the IH perturbation I've made there. So this is, you think of this as a kind of approximate automatic differentiation, where the variable h is somehow functioning as a symbolic variable. So this is not a new idea. I first saw it in a paper by Squire and Trapp in Sign Review in 1998. But in fact, the idea itself, it's not there explicitly, but the idea is really there in a paper from 1967 by Linus and Moeller that shows how you can use complex arithmetic to do all kinds of interesting things. If you've downloaded the slides from the URL I gave a moment ago, these B symbols have got links to relevant blogs if you want to know more about this topic. So the complex step method is something useful to know. It's been generalized in various ways to higher derivatives. I've used it for matrix derivatives, for Escher derivatives, and it's now quite widely used, particularly in engineering, I think. So that's a simple idea that's, I think, quite powerful. Just let me show how convince you it does work. So here's an example with arctan over 1 plus atan minus x squared. So the derivative correct to 15 figures is shown at the top. Complex step with h is 10 to the minus 100. Gets all the digits correct. If you take the forward difference with a tiny h of order 10 to the minus 16, cancellation knocks out most of the digits. And even with the optimal choice, you only get about half the digits correct. So there's something quite magical about this approximation. So this is really an instance of something that Hadamard said many years ago, that the shortest and best way between two truths of the real domain often passes through the imaginary one. So in other words, it can be worth going into the complex plane even if our problem is posed and its solution is real. So I want to stay a bit longer on this idea of complex arithmetic and think about complex functions, in particular multi-valued functions, of which the logarithm is perhaps my favorite example, and certainly a very important example. So the log of a complex number is not unique. You can add multiples, integer multiples of 2 pi I to it without changing the fact that it's a log. So I need to define which logarithm I'm interested in. And so it will be the principal logarithm. It's the one whose imaginary part lies between minus pi and pi. And this is the one that is normally of interest. It's the one that most people use. So how might we compute the principal log? Well, let's think back to the early days of computing now, to the early 1960s. So we know that Fortran was around, and it was the first language intended for scientific computing. Algol 60 had just come out. It was developed in Europe. And for a while, it was the language in which numerical algorithms were published. And so the journal Communications of the ACM, in the early 60s, at the back of each issue, there was a whole long, multiple pages with Algol programs doing useful things. Now, Algol did not have complex arithmetic built in. So what you had to do was work with the real and imaginary parts separately and do your complex computations that way. So it didn't have a built-in complex log. So Herndon wrote a little code to work out the log of a complex number, given the real and imaginary parts as input. So that's what that code does. In those days, that would have been a publication, short as it is. So just after that appeared, Ralph wrote a paper called Certification Algorithm 48, and he basically pointed out several problems with this code. Firstly, it fails for the real part being 0. The imaginary part of the computed log is on the wrong range, so it doesn't give you the principal log. And most worryingly, if you look at the line C is log C at the bottom, so log is log to the base 10 in Algol 60. It should have been ln for log to the base e. And I think what that tells us is this code had never been compiled and run. Because if it had, it would have given the wrong answer for almost any input except for z is 1. But that's understandable. This would have been submitted in late 1960. Algol 60 had barely come out. There probably weren't any compilers available. So Ralph pointed out those errors. Then Johnson and Sangren gave more discussion about division by 0 and getting the signs correct, because there was even more to say. That was followed by a paper by Collins, remarks on algorithm 48. And he noted that Johnson and Sangren, their code wrongly gave log of 0 equal to 0 and had a missing minus sign in one statement. And so finally, Collins wrote another algorithm, 243, that finally gave a correct complex log. So it took 4 years to get the log correct, and I think that's just indicative of that it is tricky working with multivalued functions. And there's a lot of things you have to get right, and especially in the old days working in batch mode, it must have been really hard to do all this work. So let me say a bit more about the log. There's a front cover of a book by Ian Stewart, 17 Equations That Changed the World. So 17 chapters, each chapter is about a particular equation. It's a really nice book. I was interviewed by the website 5 Books a while ago, and they asked me to choose my 5 favourite popular applied mathematics books, and I chose that as one of them. It's won the Euler Book Prize, and I think I saw an interview with Ian Stewart where he said that this was actually his favourite book of the many ones he's written. So the start of the chapter on the log begins with the characteristic equation there. That's the whole point of the log, that it converts multiplication into addition, of course. But in this context, x and y are thought of as real positive numbers. So what happens if x and y are complex numbers? This is a question that has arisen in my work, and I think does come up from time to time. So does that formula hold for x and y complex? Well, it's not obvious, maybe. So let's just go and grab a book off the shelf, grab a textbook, and see if you can find this formula in a textbook on complex analysis. So here's one I had, an introduction to complex analysis. So equation 9.1 says log of z1, z2 equals log of z1 plus log of z2. So it seems to be true. And there's even a little proof there. So I'm tempted to then put the book down and go and use that formula. But if I just pause a moment, I notice, oh, the proof's got a capital L log in there. I wonder what that is. Well, and there's a lowercase l for the main formula. So I'll start to think, what's going on here? If you turn the page, you'll find that it now says that 9.1 holds if you take the appropriate branch of the log in each of those 3 occurrences of log. So it's not actually an identity for the principal log. So the formula, it would seem, is not in general true. So how can we understand this and how we can then compute with this in practice? Well, and here's another example of that same phenomenon. So this is the NIST handbook. Fantastic book, successor to Abramovitz and Stegun's very widely used book on mathematical functions. It's got loads and loads of formulas in it, but just occasionally it also gives formulae where each occurrence of the multivalued function could be from a different branch. So the question then is, well, if I have a particular u and v, I want to know is for my principal branch arcsine u plus arcsine v equal to something useful. You know, what can I say? So here's a way that you can answer those questions. Something you probably haven't heard of before called the unwinding number. So the unwinding number or unwinding function of z is given by that definition. So it's z minus log of e to the z over 2 pi I, log being the principal logarithm. And if you rearrange that equation, you can see that essentially the unwinding number is the discrepancy between z and log of e to the z. So this was introduced by Corliss, Hare and Jeffrey in 1996. It does appear in a sort of more primitive form as an exercise in Apostol's famous book on complex analysis. So far it's just a definition and it's not clear why that might be useful. But at the top left, there's an alternative formula. So it turns out that you can compute the unwinding number just as the imaginary part of z minus pi over 2z and take the ceiling. So it's an integer. So the unwinding number is an integer. And interestingly, if you like to think of Riemann surfaces, it counts which surface of the which branch of the Riemann surface you're on. And so with the unwinding number, we can answer the question, when is log of e to the z equal to z? And from the formula top right, it'll be as long as the imaginary part of z is in the vertical strip between minus pi and pi, or the horizontal strip rather, between minus pi and pi. So it gives a nice answer to that question. Let me look at another interesting identity. So suppose you've been tasked with writing a function to evaluate the arc-cos of a complex number. So you go away and do that, you find the appropriate definition of principal arc-cos, which actually is not trivial, and you write up your code, you now want to test it. So what sort of test could you use? Well, certainly you would expect the cos of arc-cos z to give you back z, so that you could test that identity and see whether it's true to within some tolerance. What about the other way around? Is arc cos of z equal to z? So is that another identity I can use when testing my arc cos function? That's not so obvious now. But there is an answer in terms of the unwinding number as to when that is true. So it turns out that, except for this special case of z's there, arc cos of z is equal to this thing on the right. It's a bit of a mess, but inside there is the unwinding number. SIGN is the number that assigns +1 to z in the right half plane, and -1 to z in the left half plane. And as a corollary of that theorem, we find that arc cos of cos z is equal to z as long as the real part of z is on the interval 0 pi. So we can take any z real part between 0 and pi, any imaginary value, and we can then use that identity to test our function. Okay, so that's a nice example, I think, of where the unwinding number comes in useful. And the unwinding number can be helpful in many other identities in complex analysis. There's some nice papers by Rob Corliss on this very topic, and it also extends to matrices as well, and I've made use of it for understanding matrix multivalued functions. Another example where you can use the unwinding number is in this one here. So I want to compute the difference of two logs, log of lambda 1, log of lambda 2 minus log of lambda 1, with lambda 1 and lambda 2 complex numbers. Now the problem is that if lambda 1 and lambda 2 are close, I will get cancellation in the difference. So is there some way I can rewrite that expression to get a more accurate evaluation? Well, here's how I can do it. So let me introduce another complex variable z, lambda 2 minus lambda 1 over lambda 2 plus lambda 1. So this line in the middle writes the difference of the logs as the log of the ratio, but I need a correction term, and that's where the unwinding number comes in there. I can rewrite lambda 2 over lambda 1 in terms of z, and recognize that log of 1 plus z over 1 minus z is in fact arctan of z. And so I'm assuming I have a good arctan function. And so finally, this is what I would evaluate shown at the bottom. And you can show that that will give you an accurate estimation of the difference, even if lambda 1 and lambda 2 are close. Now, I should emphasize that z still has a lambda 2 minus lambda 1 in it, but there I'm subtracting the original numbers I was given. So this is really the best I can do. Whereas what I didn't want to do was evaluate log and then subtract, which introduces some unfortunate cancellation. So this is actually something that's used in all the state-of-the-art matrix log codes. So if you ask for the log of a matrix, this will be done at the scalar level somewhere inside one of those codes when working with the Schur triangular form. A common theme nowadays in scientific computing is low rank, recognizing low rank and exploiting it. And it really comes up in many different situations. So it's either that your data is low rank, or you want to make a low rank perturbation to some given data. And in fact, the latter is what I'm talking about here. So I'm giving myself a non-singular n by n matrix A, and I'm making a rank 1 perturbation. X and Y are vectors, so XY transpose is a rank 1 n by n matrix. And this is a well-known formula, the Sherman-Morrison formula. It goes back to at least the 1930s. I think it was discovered by statisticians originally. So again, this is something you'll find in lots of textbooks. And there it is. So it says that the inverse after making a rank 1 perturbation is a rank 1 perturbation of the inverse of the original matrix, and there's the precise formula for that rank 1 perturbation. And this has been generalized to rank p perturbations. So now U here is a vector with a matrix with p columns, likewise V. So UV transpose is a rank p perturbation to A, and so there's this more general expression now. That's usually called the Sherman-Morrison-Woodbury formula. So I often teach the Sherman-Morrison formula in my Numerical and algebra course, and I often go through it on the blackboard to check that that formula works and to derive it. And it's a lot of algebra, it's very messy, and it's very easy to sort of not see why it's true. So let me ask the question, why do these formulae hold? What's the key fact that's underlying these nice formulae? So to answer that, I'm just going to simplify. I'll look at the second one, and I will just factor out an A, essentially, from both sides. So I'll be looking at I plus a low-rank perturbation, and I've redefined the U and V as AB. So it's I plus AB, where A and B have got P columns, let's say. So it's a rank P perturbation. So that essentially is the Sherman-Morrison-Woodbury formula in that case. So why does that formula hold? So let's just check it carefully. So if I'm multiplying both sides by a plus b, I plus ab, then on the left I'll have the identity. On the right I'll get an I plus ab minus I plus ab times that second term. So and I'll put that in red. And I'll just move the a from the right of the I plus ab to the left. And then what happens is an I plus ba cancels with the inverse of the same matrix, and eventually I just get the identity. So the key formula is the one shown in red there. And if you just get rid of the a's from both sides, it's really ABA is ABA with parentheses in the right place. If I generalize that slightly, what I'm really looking at is this equation here, which I sometimes call the world's most fundamental matrix equation. And of course, it's just the associative law for matrix multiplication. So it doesn't matter where you put the brackets in the matrix product, you will get the same answer. So that's all that really is behind the Sherman-Morrison formula. That very basic fact. Okay.
Can I give a quick alternative, real quick?
Yeah.
If you were doing what people would have done in the 19th century and just expand that left thing in a geometric progression and just sort of factor everything out, it just is obvious.
Right, yeah. Yeah, so there's multiple ways of checking this formula, but I think in a sense it boils down to this equation here. So let's just look more carefully at that equation and some examples. So one I often show to my students is this example here. So a very special choice of A, B, and C. So A is a column vector X, then I've got a row vector Y transpose and a column vector Z. So we want to evaluate that product. So the answer is a vector, and there's two ways of doing the evaluation. You either put the brackets around the XY transpose, in which case you're first of all forming a matrix and then multiplying that into a vector, or you put the brackets around the Y transpose Z, and now you're forming an inner product and then scaling a vector by that inner product. So there's a massive difference in computational cost here. The first one is going to cost you order n squared operations, the second only order n. So here it makes a huge difference as to where you put the brackets, and the second is the one we would want to do. This is one of those things where if someone comes along and gives you a code and says, you know, can you make my code go faster? This is one of the things to look for, that you might be able to just do a little switch and then make someone's code go multiple times faster by recognizing that. So the general formulation of this problem is called the matrix chain multiplication problem. So you're given k matrices A1 to AK, all of possibly different dimensions as long as they conform for multiplication. And the question is, how should I evaluate that product? Where should I put the parentheses to get the most efficient evaluation? So it's a well-known problem. Computer science textbooks will typically recommend solving it by dynamic programming. There is a paper by Hu and Xing where they can solve this in order k log k operations. And that actually, I think, is the asymptotically the fastest way to solve the problem. So why is this important nowadays? Well, let's take an example where this comes up. So suppose you have a function g of x that's a composition of three other functions, f3, f2, f1. And each of these f's maps vectors of length nk to vectors of length nk plus 1. So if I want to get the derivative of g, that will be a Jacobian matrix. And if I apply the chain rule, I will get the expression shown there. So I basically get the product of the three Jacobians evaluated at appropriate arguments. And so the question now is, if I want to get the Jacobian of g, which order should I accumulate the product of Jacobians? Should I do jf3, jf2 first, or jf2, f1? Okay. So where does this come up? It comes up in automatic differentiation, where it's essentially the difference between the reverse mode and the forward mode, which in turn comes up in neural networks, in back propagation, and in deep learning. So, in other words, this simple fact that we usually take for granted of associativity of matrix multiplication is actually very important in this particular context. And there's a lovely explanation of all this in a book by Gil Strang. Gil, of course, is the first speaker tomorrow morning, and he has a great explanation. The book will be out later this year, but he already has some sample chapters on the website, and it just so happens that the chapter on this material is there right now. So if you'd like to know more about that very interesting connection, I recommend having a look at Gil's chapter from his imminent book. So here's another idea that is very useful and in some sense very simple, which is randomization. So the idea is something nasty happens for certain sets of data, And in order to try and avoid that, we can just add some noise into the problem to try and avoid those tricky cases. But of course, that might work, but you'd really like to understand what's going on and have some kind of theoretical understanding of what you're going to get if you do add noise to a problem. So the example I've chosen here is matrix functions. So I'm given an n by n matrix A. Now if A were diagonalizable, if I could compute an eigendecomposition, the lambda i's being the eigenvalues there and x having as its columns the eigenvectors, if that were possible, then f of A would simply be take f of the eigenvalues and the eigenvectors stay the same and then just multiply out and put things back together again. So given a diagonalization, it's very easy to get the any function of the matrix, for example, the exponential or the square root. The problem is, of course, this breaks down if A is not diagonalizable. And probably more seriously, if A is only just diagonalizable, you can get an x that's very ill-conditioned, and then this formula could have very large numerical errors in it. So what can you do in that case? Well, a few years ago, Brian Davis from King's College London proposed this idea. Take a random E of norm about size the unit round off times norm of A, perturb A by E, compute the eigensystem of that perturbed matrix, and with probability 1 A plus E will be diagonalizable, and now compute F from that eigendecomposition. So it's not the eigendecomposition of A you're using, but that of a slightly perturbed matrix. And importantly, Brian gave some detailed analysis in the paper that shows that you will expect to get an answer correct to about half precision. So you lose about half the digits, but this will work for essentially any A. So this gives you like a one-line formula for a function of the matrix that's reasonably good. Whereas a typical F of A code that in general will be quite long and complicated. So this is a very nice way of getting a sort of one-line quick approximation to F of A, which may be good enough for many situations, correct to about half precision. So randomization is something you'll find in fairly ubiquitous nowadays in many different contexts. This is just a very simple example for matrix functions. So the last part of the talk, I want to talk about floating point arithmetic, and I want to remind you first of all what the IEEE Standard provides. So the 1985, the original version of the standard, provided single and double precision arithmetic, 32-bit and 64-bit. The 2008 revision introduced quadruple and half precisions. So quadruple is 128 bits. Now half precision was really only defined for storage in the standard, but people, it's fairly obvious what it would have said as to how to compute with half, and people have gone ahead and implemented half in that way. So we have now this range from 16 bits to 128 bits, corresponding to about four decimal digits worth of precision in half, up to 34 digits or so in quadruple. Quite a lot of what I do is looking at the effects of rounding errors on algorithms. So I wanted to show you the standard rounding error model. So if we take two floating point numbers, x and y, and we want to add, multiply, divide, subtract them, we normally assume that the computed answer is the true answer into some error 1 plus delta. The relative error delta is bounded by the unit round off with modulus. So in IEEE double, that little u is about 10 to the minus 16. Okay, so this is the standard model that's used pretty much everywhere. And there's another variant of the model where you divide by 1 plus delta. Sometimes that's a bit more convenient algebraically to do that. What I wanted to point out, which I think isn't widely realized, is that this model is weaker than what the IEEE Standard actually says. So the IEEE Standard says to get x up y, you first of all think of forming that to infinite precision and then round it back to the destination format. So in case of double, you can think of computing x times y to at least quad, and then rounding it back to double. That's the definition of what you get. And the model is actually weaker than that. And just to emphasize that, let me show you this example. So here I've got base 10, just two digits, arithmetic in base 10. I've taken x is 9.185. So I'm just looking at rounding x into this format. So x is constant in the first column, and I'm looking at several y in the second column. The third column tells me the relative error in that approximation of y to x, and the last column is the unit round off. And the thing to note is that except for the first and last lines highlighted in pink, in every case, y has relative error less than the unit round off. So from 8.8, 8.9, all the way down to 9.6, all those values satisfy the model, but only one of them, namely 9.2, is the correctly rounded answer. Okay, so that, I think, emphasises that the model on the previous slide, which is what is almost universally used for rounding error analysis, isn't fully capturing everything in IEEE arithmetic. I'll come back to that in a moment. So let's just see how we might use that model. So if I want to compute A times B times C for real A, B and C, here's what I would do. I'd say, well, I'll do A times B. The model tells me I'll get an error delta 1. Then I'll multiply by C. That will give me an error delta 2. And both delta 1 and delta 2 are bounded by round off. Okay? So then I can just multiply out. I've got a 1 plus delta 1 times 1 plus delta 2. I'll expand and I'll drop the second order term because U is small, so delta 2, delta 1 is small compared with delta 1 and delta 2. And so roughly speaking, the error in the worst case, the error will be about order 2U. So the precision of the individual operations is U, but the accuracy in this case is probably as bad as 2U. You can imagine if I was doing thousands of operations here, the accuracy would now be some much larger multiple of U in its worst case. So it's very tempting to say that accuracy is always worse than precision, based on that sort of example. But of course that's not actually true. Accuracy is not limited by precision because we can always simulate higher precision arithmetic with the arithmetic of a given precision. And that's something that I think is often forgotten. So just let me emphasize that with a little story. So this is Stan, the Tyrannosaurus Rex. He's from Utah originally, but he now lives in the Manchester Museum, just across the road from my office. And the story is that a tourist asked the museum attendant, how old is Stan? And the attendant said, 100 million in 3 years. And so the tourist said, well, how can you be so sure? He said, well, I've been working here 3 years. He was 100 million years old when I got here. So that's precision versus accuracy for you. Now, we work very hard to get accurate answers. And it's just worth bearing in mind that often the data is not very accurate, and for some surprising reasons. So you may or may not have heard of this example, but a German computer scientist a few years ago discovered that a certain Xerox photocopier was contaminating the results when it was photocopying. So the left 2 columns are the original, the right 2 columns are the photocopied version, and the fourth digit has been changed from 6 to 8 in several cases. And this of course, this is really an error in scanning and image processing, and it was traced to a problem with the J-big2 compression algorithm. So you wouldn't expect photocopying or scanning to introduce errors, but it can do. And sometimes it's just human error. So this website Retraction Watch reports papers that have been retracted, and there's a lot of them. And this one was retracted because 16 had been entered as 6 incorrectly in some of the data. And the argument is because the person didn't press the 1 key hard enough. So that, again, a major relative error, much larger than the ones that we are normally dealing with. So we have to keep in mind that the data isn't always accurate. So I want to talk just briefly about low precision arithmetic, and this is something that I'm thinking a lot about at the moment. And this is motivated by the increasing availability of low precision in hardware. So low precision, or half precision particularly, we saw is actually in the IEEE Standard now, and it can bring several benefits. First of all, arithmetic in low precision should be faster than in high precision. We've now got less data to move around if we're dealing with half precision variables, so that can obviously bring benefits as well. There's less storage required, and also lower energy consumption, so potentially lots of gains by going to lower precision. The NVIDIA V100, which came out last year, is particularly interesting here. So this is a GPU that provides double, single and half. Single runs twice as fast as double, which is normally the case nowadays. But on this particular GPU, half can run up to 8 times faster than single precision in the absolute peak case. And the reason it's so fast is that this has some built-in tensor cores. So the V100 can do A times B plus C, where A, B and C are 4 by 4 matrices. It can do that in 1 clock cycle. That's 128 floating point operations in 1 clock cycle. And it can even return the answer in single precision as well. Okay. The top 500 that came out last June, 2 months ago, had a new number one computer. It previously been occupied by a Chinese machine, but now there's a US machine called Summit at Oak Ridge National Laboratory, which is officially the fastest computer in the world. And it's got 4,608 nodes, and each node has 6 of these NVIDIA V100s on it. That's 27,000 V100s. So clearly, if you're going to exploit that machine to the full, you want to be trying to exploit the half precision that it can do very fast on each of the GPUs. So, why is half precision, where is it of interest nowadays? Well, clearly machine learning is probably the main driver. And I've been tracking the literature for a few years now, and over the last 3 or 4 years, there's more and more papers where people are saying that in machine learning, you can train and run the algorithms in half precision and get very good answers. So half precision has been experimentally found to work very well in many cases in machine learning. But another example that's less well known is in climate modelling. Tim Palmer, who's a professor at the University of Oxford, has been for a number of years now advocating the use of low precision in climate modelling. And his argument is that just in certain parts of a climate model, he would like to use low precision in order to get a more fine-grained resolution of the grid. He will give up some accuracy of the grid, but he'll get a finer grid. And the argument is that that will give you more useful results. And Tim's written a number of papers in recent years on this topic, and he's been advocating this for quite a while now. So those are 2 examples where this is being used, and I think in scientific computing more generally, people are starting to think about how they can exploit half precision, given the benefits I mentioned a moment ago. But let's just think about error analysis for a moment. So suppose I want to compute the inner product of 2 n vectors, x and y. What I'm showing here is the standard rounding error bound. So it says the computed answer minus the true answer is bounded in modulus by n, the problem dimension, times the unit round off times mod x transpose y, plus second order terms. Now in half precision, little u, the unit round off, is about 10 to the minus 4. So that constant nu is already 1 for n about 2000. So once you get beyond 2000 for the size of your vectors, the standard error analysis doesn't guarantee any correct figures at all in the computed inner product. So this is clearly a concern. If we're going to start using half precision in scientific computing, we do have to worry about whether we're going to get the right answer or not. And that would suggest that there could be problems for quite small n. So what can we say? And this is early days really of investigating this, but I've got a few comments and suggestions here. So first of all, one thing you can do is use a fused multiply add. So an FMA is where you can do x times y plus z in a single operation and with a single rounding error. So rather than having 2 rounding errors, one for the multiply and one for the add, you just get 1 rounding error. And so by using that FMA, you basically can reduce your error bounds by a factor 2. So that's a small help. As we saw, the V100 does have an FMA for the tensor core matrix products. Pairwise summation. So when you want to sum n numbers, like in the result from the inner product, rather than do it sequentially, you can do it in a tree structure. So if you had 8 numbers to sum, you could do it, add the first 2, the last 2, add them in pairs, then add those results in pairs and form a binary tree where the answer would be at the root of the tree. And it turns out that the error constant goes down from n to log 2n in that case. So the rounding error bound is improved from n to log 2n. We can also exploit whatever the hardware might provide in terms of more accurate results. So on the V100, you can get the output from a half precision operation as a single precision result. Because it accumulates the products and so on in single precision. So that gives you a much more accurate result than you would otherwise have expected. And more generally, what you might try to do is use your initial approximation computed in half precision as just an approximation and then refine it using higher precision. So use that as a starting value for some higher precision computation. And I've done some work recently on this with Aaron Carson. And we've been looking at iterative refinement for solving linear systems of equations. And the basic idea is that we will, A is given as double precision, we'll factorize A and solve in half precision, use that initial approximation, and we'll refine it in double precision. But most of the work is in the LU factorization, so most of the work is being done in half precision now. And working with Jack Dangaro and colleagues at UT Knoxville, this has been implemented, and we find it can give about a factor 4 speed up over the best current X equals B solvers in double precision, at least for matrices that are not tool conditioned. Condition numbers up to about maybe 10 to the 8 or so. So that's one approach you can apply. But there's a whole different perspective on this, which is, I was showing you a worst case error bound a moment ago, and you might argue, well, that worst case where I had an n times u is not really attainable. It's not possible for all the rounding errors to add up to give that constant. So, two things you might think about. So I mentioned earlier that the model is not actually telling you everything about the arithmetic. Is there some way you can actually do a better analysis by exploiting correct rounding? I think that's pretty difficult, but it might be possible. And also something I'm looking at with my colleagues right now is statistical analysis. So rather than go for worst case bounds, if you make some assumptions on the distribution of rounding errors, you can then try and obtain more like average case bounds and say, on average, this is what you'd expect the error to be like. This is not a new idea. It goes back to the 1950s and 60s. Peter Henrici, Tom Hull. There are a number of papers by people like that on this topic. But it's rather fallen out of favour in recent years. But I think particularly with the increasing use of half precision, I think it's worth looking at again. And so one thing my colleagues and I are currently thinking about is, can we do anything new in terms of statistical analysis? So to finish up, just a summary of what I've been talking about. So complex arithmetic is useful, even if we're only working with real variables. It can be a good idea to take a step into the complex plane and do things there, then come back. We saw that with the complex step approximation. The associativity of matrix multiplication is a very fundamental property that we tend to take for granted, but actually it's very important. And in Jihao Chen's talk yesterday on parallel prefix, I noticed that associativity also played a really major role there as well. So it really is an important concept that we need to keep in mind. Randomization is always useful, just throwing a bit of noise into the problem, but you do want to really make sure you understand what you're doing when you throw that noise in. And then finally, low precision. Yes, it's increasingly available now. People are starting to use it. We just want to make sure that we are getting answers of sufficient quality when we work to, well, initially we have 4 significant digits. You know, we can't afford to lose too much if we want to get reliable answers. So I'll finish there. Thank you very much.
Thanks for a great talk. Do you have any questions?
So I was interested in the randomly perturb a matrix and get something that's better conditioned. So how can you guard against the possibility that your perturbation makes the combination worse, you know, more ill-conditioned than the original case, right? What if you start away from that danger zone and your perturbation actually brings you there?
Well, that could happen, but it's one of these probability arguments. With probability 1, it won't happen. So you could just be very unlucky. And that's life. This is the way.
Do it twice. And then
Yeah. Yeah.
Yeah, very interesting talk. One thing that we've been working with in our differential equation solvers is we've been comparing different methods like these against each other, and we've been trying to find out is there some idea to be able to compare work, right? One of these ideas is in some cases for dealing with catastrophic cancellation, you can use you can instead calculate something by using the contour integral instead of directly computing it, or you can use higher precision. And so what we found is that in some cases using higher precision can make your computation faster, or sometimes using this contour integral and going into the complex plane, it can make it faster. And we tried to ask the question of in which cases is which one better, and we just couldn't find a good answer. So I was wondering if there's any models of once alternative numbers start coming into play, can you start estimating how much work you're actually going to be doing, and which trick of these might be doing better or worse in given cases?
Well, very interesting application there. It's hard to say much without knowing a lot more about it. But all I would say is I do use high precision quite a bit, actually. So quad precision, though, is only available in software at the moment. But as long as you're only using a little bit of it, then of course that will be acceptable probably. So I guess you would just require some analysis, and I'm not quite sure what to suggest for your particular application. Other than to say, yeah, I think those are both very good ideas to try, and it's not clear to me which would be better.
I was wondering if the fact that half precision is only 16 bits allows you to do things like just brute force check the distribution of certain operations. So I mean, if you know, it's 65,000 results for a single operation function, and then even a reasonable amount that you could check for a 2-argument function.
Yeah, well, very interesting point, which I didn't touch on at all, but there aren't many numbers in the FP16 system, and there's all kinds of implications for that, not least of which is overflow. So just rounding a matrix from double to half precision, for real-life matrices, you're quite likely to get overflow, and then the question is, how do you handle that? Another example is the famous example of summing the harmonic series, sigma 1 over n, for n is 1 to infinity, which we know mathematically diverges, but in floating point it will eventually converge, but you have to run it an awful long while in single or double. If you run that in half, it will, in a flash it will have converged, just because it's so low precision. So many things are different in half precision, and as you say, there's a lot more to be said, in particular the fact that it's a very small set of numbers.
One last question.
You commented that low precision arithmetic consumes less power. Could you comment a bit more on that? I believe that we could produce an exascale machine today, but the power consumption would be unbelievable. I believe the goal is that an exascale computer would consume less than 30 megawatts. Do you, at the moment we benchmark in terms of time, there's very good benchmarking macros within Julia, which we've seen used here, and we benchmark in terms of length of the computation, time consumption. Do you think in future people will be benchmarking in terms of power consumption per computation?
Well, I'm not an expert on this, but I know there's recent work by Jack Bangara and his team where they instrument the processor and the GPUs, and they have shown that in the AX equals B application I mentioned, that you do get power benefits to that idea I mentioned of iterative refinement. So they've shown there are real benefits there. So I think yes, so this can bring significant benefits if we can extend that idea to a whole range of algorithms.
Great talk.